Hello everybody, my name is Fiore. I am the team lead of the Magnetic Heater Design Group. Myself, Guidwo, Sinord, Ersen'S, and Joshua Letizia will be presenting our Capstone project. And in the next slide, we'll show our project video.
Hey, I'm Ersen'S.
Hey, I'm Guy.
Hi, I'm Josh.
Hi, I'm Dr.
And we are the Magnetic Heater Design Team.
Dr. Bhowmick and Dr. Shen, mechanical engineering faculty at UMass Dartmouth, have been working in biomedical research towards a new drug delivery system that targets a diseased area and releases medication on demand. This is done by constructing a small patch that is then placed directly on the diseased area. This could be a tumor, an organ, or anywhere inside the body. This patch contains small polymer fibers that have a medication and small conductive particles known as magnetic nanoparticles. When this patch is exposed to induction heat, the small conductive particles heat up and the polymer chains break down. This releases a small amount of medication into the diseased area and has the ability to control exactly how much medication is released and at what time.
Dr. Bhowmick and his PhD student have demonstrated the effectiveness of releasing medication on demand in vitro, which is outside of our living organism, or just in a test tube. The next step in furthering this research is demonstrating the effectiveness of the targeted drug delivery system in mouse models. But the induction heating system in the lab is not capable of producing a strong enough magnetic field to penetrate the mouse. Due to the fact that we're working with the same power generator, the focus of our solution to the issue comes down to the induction coil. And with this induction coil, we want to demonstrate a stronger magnetic field that accommodates abnormals and also capable of producing more heat within the magnetic nanoparticles than the existing induction coil.
We utilized different techniques in order to build our desired induction coil. These techniques are built around use of software such as Console and SolidWorks. We also utilize measurements recorded in the lab to record the magnetic field and heat of the drug delivery system. Console allowed the team to conduct theoretical measurements, while SolidWorks allowed the team to design and fabricate different prototypes to test in the lab. The fabrication and analysis of these models allowed the team to ensure the parameters set by the problem statement were being followed.
Throughout the project, we experimented with different coil designs and materials that were not capable of producing a stronger magnetic field. However, these experiments helped us understand the topic better than before and allowed us to optimize the design to its fullest capability. We developed an induction coil that produces a stronger magnetic field, increases the heat generation in the magnetic nanoparticle, and allows us more of the mouse to be covered. We would like to thank our sponsors, Dr. Sankha Bhowmick and Dr. Caiwei Shen, for providing resources and equipment to make this project possible.
We had mentioned in the project video that the faculty we are working with on this project is Dr. Sankha Bhowmick and Dr. Caiwei Shen, both mechanical engineering faculty here at UMass Dartmouth. Dr. Bhowmick had advised a PhD student that demonstrated the use of induction heating for on-demand drug delivery. This was tested outside living organisms, but their goal is to test inside living organisms such as a mouse. But the induction coil used in these experiments do not produce a strong enough magnetic field to penetrate the mouse's diseased area. So our goal is to design an induction coil that produces a stronger magnetic field, and to demonstrate this by recording the temperature rise of the drug delivery system shown in the video. The same power generator and heat station will be utilized throughout this project, which can be seen in the figure in the slide. And for those who don't know, when an alternating current is sent to a coil that's typically copper, a magnetic field is generated around the coil, and conductive material heats up when it enters the space of the magnetic field.
Like mentioned in the video, because the focus of this project, our design is solely the induction coil, we could not change anything, any specifications related to the power generator. So the limit of the power generated we need to consider for our design. Another consideration is the size of the mouse that is shown in the figure. So we have to work with these two sides of the mouse. And this figure is the dipole induction coil. The two most important dimensions are the diameter and the number. So the team brainstormed like different geometry of coils that can give us a solution. Like you can see oval, flat, rectangular, and circular coil. Circular coil was chosen due to the fact we can get maximum flux linkage, and also it is better resist against magnetic forces. And moving forward, the team needed to understand what parameters need to be changed to increase the magnetic field generation. Values of equations that you can see on the screen shows that as long as we keep the currents, as long as we keep the current the same, the only thing we have to worry about that might affect the magnetic field is the diameter and the number of turns. Also, we know that the circuit like between our station and our coil design looks similar to this figure, which is a RC circuit. From the equations, from the RC circuit equations, the impedance will increase as we increase the number of turns. This actually will be able to take full advantage of the maximum current from the generator. But as we increase the impedance, the power and voltage will increase with it and make us both the power and voltage kind of attain their limit. So from that we won't be able to take full advantage of the maximum current from the generator. And the team could not approximate the power and voltage of the generator because there is like too many values of the capacities that were used to us. So we just assume the generator will be able to handle it, and we designed this to be a induction coils overall the same.
In terms of the simulation itself, taking the 3 induction coils that we created and the governing equations that we had, we actually incorporated these design parameters into our new simulation software that we had utilizing console. Utilizing console, we were actually able to take the designs and actually measure the magnetic field that will occur in these designs. In terms of the parameter set in the actual design, we used pure copper and then the surroundings air. This was just to model itself after the actual lab space that we're using. And then the values itself, if you can see up there, the dark blue area is actually the center of the coil, and we actually took the dark blue area to be the direct center, to be the value of that magnetic field. Doing so for each of the 3 designs and the control sample itself, we were actually able to mark in the graph seen on the right. And noticing the trend, we actually went on to the prototyping stage to continue and actually measure these voltage depending on these magnetic fields. In terms of prototyping itself, we went from console, and then to ensure that the console dimensions that we designated were to be followed, we actually incorporated the design into a SolidWorks CAD model, which essentially made the same coil that we had designated in the console, and we were able to make the dimensions that we wanted to follow to be exact of the dimensions that we specified in the console. And in doing so, you can see the actual process of making it, and then the bottom process is actually all the fabricated models that we were able to make.
Two experimental techniques were utilized to demonstrate the effectiveness of our new induction coils. Sorry about that. We first used a wire wrapped around a PVC pipe as a field pickup coil. We then attached each ends of the wire to the negative and positive terminals of a multimeter, which both of those can be seen in the figures in this slide. We then placed the pickup coil in the center of the induction coil, and we measured the peak voltage induced in the field pickup coil. We then used the equation shown to calculate the magnetic field. And we immediately did this for the existing coil in the lab, and we had measured a magnetic field of 25 milliteslas on a maximum current of 452.5 amps. And this value acted as our control, and the same method was used by the supplier of our induction heating system. The next technique was measuring the temperature rise of the drug delivery system itself. So the drug delivery system was fabricated with 33 milligrams of conductive nanoparticles. It was then placed in 1 milliliter PBS, and we then, PBS is just a salt solution used to simulate inside of the body. We then took the temperature every minute for 10 minutes using a fiber optic temperature sensor, and the same drug delivery system was used throughout the project to reduce any variation between samples. So the team then prototyped the 3 new induction coils using a nickel-copper alloy instead of pure copper. The team decided to use this material first because it was resistant to corrosion, it was cheaper than pure copper, and it was stronger, so it wouldn't be prone to any kinks during prototyping. We then used the first experimental technique to measure the magnetic field of our induction coils using the nickel copper. And we found that these coils could hardly produce a stronger magnetic field than the existing coil in the lab, and that is represented in the bar graph in orange as the control. We also noticed that the 3 new induction coils were causing the voltage to peak before we could take full advantage of the maximum current. And this was very important because the magnetic field strength is dependent on the maximum current we can extract from the generator. And this is shown in the next graph where, again, our control is represented in orange and our 3 new induction coils are represented in blue.
So due to the fact that the nickel copper material not working well with our design specifications, we went back to the actual pure copper design. In terms of the results of that, it actually turned out that the pure copper allowed us to maximize the current, and which allowed us to actually maximize the magnetic field generated in this material. The control sample you see in the orange, we actually were able to get almost some of the new coils that we created were actually achieving almost double the value of the magnetic field. And then we also did it on the second experiment test for temperature rise, and we also saw almost double jump in the temperature rise as well. In terms of the actual designs that we went on to decide for the final solution were the 3.6 6-turn and the 5 centimeter 6-turn coil. However, in the final solution itself, we went with the 5 centimeter 6-turn coil due to the fact that it jumped from 25 milliteslas to 40 milliteslas and increased the heating from 6.9 Celsius to 14.1 Celsius. However, due to the fact that it's a 5 centimeter, it actually worked well with the 2 different mouse specimens that we had. The 3.6 would not be able to fit some of the mouse specimens that we had due to the fact that the full dose size is roughly around 4.5 centimeters. So it works well with both devices, but also due to the fact that it's a 6-turn, it increases the coverage of the actual in vitro testing itself.
So here we have a list of the bill of materials. Provided with a $1,000 budget, we were able to spend $350 of it, purchasing all the necessary tools and equipment for the project. Areas where we felt like we could have reduced the total cost was to initially purchase the nickel copper alloy material instead of the pure copper, due to the nickel copper alloy costing 99 cents per foot, as opposed to pure copper costing 188 per foot. And here we have a project overview of what was accomplished in each gate. The first few gates were dedicated primarily to design and theoretical analysis, while the remaining gates were dedicated mostly to prototyping and experimental testing. And for the future work, would include the inclusion of a containment cell. It will feature some variant of a carriage-like design, as you can see. It will be used to store in vivo specimens, as well as experimental biogels and biofluids. It will be a simplistic design it'll be a simplistic design to fit within the induction coil, not only to ensure that the containment does not touch the actual induction coil, but also be able to scale it up and down for larger and smaller diameter induction coils. And we also want to send special thanks to our sponsors, well, advisors, Dr. Sankha Bhowmick and Dr. Caiwei Shen. We also want to thank Dr. Sinord for guiding us through the process of the Capstone. We want to thank Paul Sosa, as well as Tom Foster, for allowing us to use the machine shop, as well as the 3D printer to prototype a lot of the components that we needed. And we also want to thank the alumni, Yasmin Hamadani, for laying the groundwork of the program.